This is my lab report for lab number 3. This lab describes an object we are given as a star orbiting a black hole, and our job in this lab is to estimate the mass of that black hole. So what we're going to do is create a glow script program to simulate a randomly generated motion of that star. Using the motion of that star, we're going to find the net force on the star for all the data points. We know that the net force is only due to the force of gravity of the black hole, and the time between each data point is going to be 1 day or 86,400 seconds. So then using this net force, we are able to estimate the mass of that black hole. So setting up GlowScript, we take the given sample code lab3. I am going to input in my username to create a unique motion of travel for that star. That star is our system in this lab, the mass of it being 2 times 10 to the 30th kilograms. And then our surroundings for the star is just the black hole. We do not know the mass of that because we were trying to calculate it. We know that the change in time is also 86,400 seconds. Since the net force is just the force of gravity as given, we are going to use Newton's law of universal gravitation to find the mass of the black hole. So we can just input the net force wherever the force of gravity would be in this equation. So we can say that the net force is equal to Newton's gravitational constant times the mass of the black hole times the mass of the star, all divided by the distance between the two squared. And then we can rearrange this equation to give us the mass of the black hole is equal to the net force times the distance between the two, divided by the gravitational constant times the mass of our star. So to continue to set up GlowScript, to compute the initial and final momentum vectors, we use the momentum formula. We were also able to find the net force by using the momentum force formula, which is the net force is equal to the change in the momentum vector divided by the change in time. We were able to calculate the parallel components and the perpendicular components of this force. We know that the parallel components deal with the change in the magnitude and the perpendicular components deal with the change in direction. So I was able to calculate these in lines 177, 178, and 179, and then input these finally into lines 182, 185, and 188 as the net force parallel and the net force perpendicular. And then finally, like I said, the mass of the black hole is derived from Newton's gravitational law, as said in the previous slide. So I was able to then take all of the variables that I defined up above and then input that into an equation on line 193 to generate the mass of the black hole. I also added vector arrows that will run during the running of the model, and those will be shown by arrows in the model to show the parallel and perpendicular components. So here are a couple screenshots of my model through GlowScript. As you can see on the left, the model is in the middle of running, so you can see pretty well the perpendicular and parallel components of the motion of the star. And then on the right, you can see that the star has completed its revolution, and I was able to find the net force in the parallel perpendicular components, and then I'm now able to estimate the mass of the black hole. So what does this all mean? That means that I am now able to, using the data points, estimate and average the mass of the black hole, which I got to be 1.51 times 10 to the 34th kilograms. We also know that the net force and the rate of change in momentum, which is the change of the momentum vector divided by the change in time, are the same thing. So that means that the parallel components both deal with the change in magnitude of the momentum, and the perpendicular components of both deal with the change in direction of the momentum. So then we have one what if question. And what if the black hole was replaced with a new one? However, the momentum or the motion of the star and the net force did not change. Unless we introduce a new force other than gravity, it is not possible for that new black hole to have a different mass. That's because the motion is going to remain uniform. So that means that our velocity is going to remain the same. We're already assuming that our sun's mass is also remaining the same, so therefore the momentum has to be the same as well. So as we see with our net force equation, the net force is equal to the change in the momentum vector divided by the change in time. Neither of the variables, the time variable or the momentum variable, are going to change. So that means that our net force therefore cannot change. So the mass of the black hole must be the same. And that's it. Thank you.